Hello, my name is Vandierendonck and I would like to talk to you about software-defined floating-point number formats and their application to graph processing. This is research performed at Queen's University, Belfast. In graph processing or graph analytics, it's well known that many of the memory accesses are following a random or pseudo-random access pattern. Because of the large data sets that are involved, most of these random memory accesses actually have to be served from the main memory, also known as DRAM, rather than being served by the on-chip caches. And the performance difference between these two types of memories is extremely large. To give an indication as to how big the problem is, we have shown here a number of graph datasets which are commonly considered in academic research. And shown some statistics on their size in terms of the number of vertices and edges. Then during a graph analytics operation, what will typically happen is that we will create one or more very long arrays of vertex properties where for every vertex we have one property. The properties themselves are typically small, for instance 4 bytes per element, but multiplying by the large number of vertices in these graphs, we end up with very, very long arrays. And if we compare how long these arrays are in comparison to the last level caches on modern server processors, we can see these are multiple times larger. In fact, for the ClueWeb graph, we can see that the array that we are trying to access using random accesses is almost 300 times larger than the amount of memory that can be held on chip. The consequence thus is that we can only manage to hold a very small amount of data because of capacity. So the premise of this work is that we want to compact the vertex properties in these applications. And the idea is very simple. If we can compact them, we can fit more elements in the cache, and that means we can serve more memory access instructions from the cache, which is faster than the memory. The speedups we can obtain by this are illustrated in the plot on the right hand side, so between 30 and 50% for PageRank, between 20 and 50% for accelerated PageRank. The delta stepping single source shortest path algorithm has a bit lesser speedups. And then for the maximum independent set problem, we can have a substantial speedup over 100% faster. So this is the type of result we can obtain by making the vertex properties more compact. So why is this hard? This is hard because if you work with applications with floating point number formats, then there's no hardware support or generic hardware support for 16-bit floating point arithmetic. These types of arithmetic have not been standardized yet. As such, some kind of software emulation will be necessary, but practice has shown that software emulation of floating point arithmetic is very slow. In fact, it can slow down applications by orders of magnitude. Another problem is numeric stability of the calculations. So if we use 16-bit floating point number formats, then we have to make a careful trade-off between how many exponent bits we will have and how many significant bits we will have in that format. This becomes very sensitive to the application because of the very narrow size of the floating point number. In fact, in the domain of deep neural networks, which is very compute intensive on floating point arithmetic, different 16-bit formats have been proposed, which are slightly different in how many bits they assign to exponent and significant, which affects the range and the precision of these numbers. And this shows that depending on which algorithms we would like to implement, or depending on performance versus accuracy concerns, one would desire to use different floating point formats at this narrow length. The solution that we propose is to have software-defined number formats, and the advantage of this is that the format can be carefully tuned to the application demand, such that we can ensure that the number format is useful and will lead to accurate results. Moreover, we will implement a conversion of these narrow number formats to hardware-supported formats to leverage the existing floating point hardware. This is essentially the same technique that is often used in software emulation, but we will see how we can make this faster than what is usually done in software emulation tools. So the agenda for this talk is that after the introduction given so far, we will talk more about what the software-defined number formats are. We will then show how they can be applied to graph analytics problems, and we'll show an experimental evaluation. So the software-defined number formats are inspired by the floating point standard IEEE 754, which defines a floating point number using a number of fields, namely a sign bit, an exponent, which is an integer encoded in a bias notation, and a number of significant bits, which determine the precision of the numbers. These formats are actually storage formats, and so they determine how a number is represented in a sequence of bits, and they don't necessarily prescribe how they should be operated on using by the arithmetic units. So what we will do is we will propose flexible number formats which can be defined by the software, and where there is a conversion method to the hardware supported formats. For this reason, we use formats which are very similar to the hardware existing ones, such that we can minimize the effort of conversion. There are also special cases in floating point numbers, which are specific bit patterns where the meaning of the bit pattern deviates from the sign exponent significant pattern. And these special cases are things such as not a number representations, which could be signaling or quiet. We have plus and minus infinity, we have a positive and a negative zero, denormalized number, rounding modes, exception handling, and so on. And so all of these special cases, they add a lot of complexity, especially in software emulation. So what we will do is we'll define a format which consists of a flag describing whether or not we have a sign bit, because if we don't need a sign bit in the numbers, we don't need to carry this. We will have a number of exponent bits, a number of significant bits. We will have a flag indicating whether we want support for a zero or not, and we'll only assume a positive zero in this work. And we also have an additional exponent bias. As far as the special cases go, we try to avoid implementing any logic at all to deal with these special cases under the assumption that they will not occur in the applications that we have. So this requires some careful analysis to determine that this is the case. A very important idea behind the number formats and the conversion was made by a colleague at Queen's who observed that bit patterns in the numbers very often remain the same. In particular, this relates to the exponent, where the high order bits are constant under certain conditions of the values that we're trying to represent. Specifically, if you want to represent numbers that are less than 1 but larger than a certain value, then all of the exponents, then we can determine that the high order bits follow a specific pattern. This then means that we can actually truncate the exponent when we compact the number format, because we understand what bits have been removed. For the significant, we truncate the least significant bits, which is a fairly straightforward operation. Using these methods, we can actually convert floating point numbers using truncation and bit selection only, and we can avoid arithmetic operations, which would be more potentially more complex. Another issue we need to look at carefully is data movement. And so this specifically relates to the architecture of the x86-64 systems, where we have a set of scalar registers where we can perform operations on single values, but we can only perform integer operations within these register sets. Next to that, we also have vector registers, where a single vector register effectively has multiple lanes and so packs multiple values inside a single register. There's then support in the hardware to perform operations on a lane-by-lane basis, or sometimes operations where values are moved across lanes. Floating point values in this instruction set are always mapped onto the lowest ranked lane within a vector register. So this means if we are reading a value from memory and then want to convert that value to a standard floating point value on which you can perform arithmetic, it means that that value will need to end up in a vector register eventually. And then there are different ways we might write code to achieve this. A straightforward way is using what is known as a union trick in C or C++, where we declare that two variables of a different type actually share the same memory location. Then making the conversion using the union trick would typically result in the compiler generating code where the value is first read into a scalar register. Then we use the scalar registers and the associated instructions to convert the value to the correct bit pattern, so to convert a 16-bit pattern into a full 32-bit pattern that corresponds to a floating point number. And then using the union trick, we would have to write this back to memory and then read it back again using the vector register instruction set. The data movement throughout this path would correspond to about 8 cycles typically on a Skylake X processor. We can also take a shortcut. Rather than using the union trick, do a direct scalar to vector move instruction. In this case, we can reduce the data movement latency to 5 cycles. Or we could directly operate on a vector lane by issuing vector instructions, which would mean we'll have to manually write those codes. If we operate directly on the vector lanes, then data movement between memory and the registers would be reduced to 3 cycles. Now, since we are already working in the vector register set, we might as well consider vectorizing the operation. And the advantage here is that using a single instruction, we could, for instance, operate on 8 vector lanes concurrently, which means that the data movement of 3 cycles is actually amortized across 8 different lanes. So that means that the average number of cycles per element that is being operated on is reduced. In other cases, we would use gather operations. So when the values we are reading are not consecutive in memory, but typically for the random access patterns seen in graph analytics, we would have to fetch them from many different locations and then combine into a vector. These take a bit more time, but we would still have a good efficiency. So these are things that we need to consider in the implementation. So the union trick isn't in itself very efficient. We need to really consider better utilization of the hardware. There's another issue we need to keep in mind, is that of data width. Whenever in a vector register we want to converge, for instance, a vector of 16-bit fields into a vector of 32-bit fields, then the latency for this will typically be 3 cycles. And the reason is related to how the vector registers are implemented. Essentially, AVX2 and AVX512 vector registers are implemented as chunks of 128-bit SSE registers, and any conversion of the width of different elements will trigger data movement across those 128-bit groups, which takes 3 cycles. Now, an important trick here is that we can use a gather operation to load values, and it means we can actually compose those values such that they immediately land into 32-bit lanes. It's a very simple trick. Rather than loading 16 bits, we load 32 bits. And that then simplifies the conversion, takes a little bit more latency out. If you put everything together, then for one particular format, which is really the minimal case we have considered, in terms of the features of the number formats that are supported, where we'd normally have a gather operation shown here to load a set of values from memory. In this case, in order to convert 16-bit floating point numbers to 32-bit floating point numbers, we would need to issue 2 additional instructions to make the conversion to a floating point number, to a valid floating point number. Those 2 instructions each have a single cycle latency. So this is a minimal addition to the latency of the data fetch and conversion. And we will see actually that this still has a measurable impact. So now that we have an idea how we can implement software-defined numbers and how we can convert them to hardware-supported numbers, we can see what kind of number formats we would have to define for specific applications. And basically what we propose here is a process based on analysis of the code and an analysis of the numbers that appear in the code. So for the PageRank code, which is shown here on the right in some pseudocode, this is an algorithm based on a PhD dissertation within the space of numerical analysis. And so this algorithm has been vetted and designed very carefully to be numerically stable. Within this algorithm, the major step is the red line, which essentially corresponds to a sparse matrix vector multiplication, whereby all of the weights in the matrix are 1. So the multiplications are moot, and we essentially just add up a number of values from the vector C to compose the elements of the vector Y. If we look at this code, then there's a number of things we can observe about the elements of the vector C. Essentially, these elements are preliminary PageRank values or estimates for the PageRank values, and they are divided by the degree of a vertex. So if you then work through what this means, then, well, we know for PageRank values that they are always less than 1, and that they are larger than 1 minus d divided by n, where d is the damping factor that we want to apply for the PageRank calculation, and n is the number of vertices. This follows from the algorithm and the structure of the problem. So this defines essentially the range within which we have to represent numbers. And this constrains then the number of exponent bits we require. The number of significant bits can actually have to grow throughout the algorithm. So depending on how accurately we want to calculate the PageRank values, so how many bits of accuracy that we need, we will potentially start off with initially very few significant bits during the calculation, and as the calculation grows, additional bits in the significant are being filled in with accurate values. So as the calculation proceeds, so as we do more iterations of the outer loop in this algorithm, we may need to grow the representation to have more significant bits. So that means we can run a number of iterations in 16-bit precision, and then eventually we'll need to switch to a 32-bit format. Now, going back to the 16-bit format, we can argue that based on the properties of the PageRank numbers that we've given, that 6 exponent bits will suffice if the number of vertices is less than a certain value, which is essentially 2 to the power of 32 times some value dependent on the damping factor. Now that's a very loose upper bound because it assumes that the worst case degree of a vertex would be n, but in practice the degrees are less than the square root of n, and so we can actually represent larger graphs or operate correctly on graphs larger than the number of vertices given here if we assume 6 exponent bits. So in order to make up a 16-bit format, we have 6 exponent bits and 10 significant bits. So there's a process that we've presented for the PageRank problem, and we have applied a similar process to some other graph algorithm problems. So we did this for accelerated PageRank, which is a variation on the PageRank problem that carries through differences in the PageRank values rather than the actual values themselves, and that changes the range of the numbers that we will be working on. In fact, it also changes the nature of convergence because it means that initially we need to work with more accurate numbers that are being carried through, and later on, because the numbers get smaller and less significant as they go along, we can work with fewer significant bits. This is essentially because there are the differences from one iteration to the next. And as the program converges, those differences become smaller. We have a different format for delta stepping single source shortest paths. In this case, there's actually a caveat that this works, but is dependent on the range of the weights in the graphs, obviously, but also dependent on the diameter of the graphs. If you have a high diameter, then it tends to be the case that rounding errors in the floating point arithmetic start to add up. And then a 16-bit floating point format is simply not very resilient to those rounding errors. Finally, we've also looked at an integer-based application, which is a maximum independent set problem. And so in this case, vertex properties consist of one of four states. And so 4 states can be encoded into a 2-bit integer, but general programming languages don't allow you to encode integers easily into 2 bits. You have to do some manual intervention to compact or to encode the data correctly here. In this case, we've extended the techniques we have looked at, so especially the data movement throughout the register sets within the system in order to obtain a very efficient conversion for this problem. So additionally, we've also looked at bit masks, so for frontiers, they represent sets of vertices that are active or should be considered that. So these sets can be encoded typically as bit masks. We could also encode them as array of bools, of Boolean values, and we could also encode them as bit masks, which is the convention in the AVX2 instruction set to encode conditional values or true-false values. So finally, then some experimental evaluation. So we show here results for PageRank, accelerated PageRank. More details are in the paper, and we also look at just 2 of the graphs that we have considered. We compare the PageRank value to an implementation in the GAP benchmark suite, which is considered a good standard of comparison. So we look here at the SPMV-based code, and we observe that for the Twitter graph, the baseline Graptor code that we use, so we've implemented in a vectorized graph processing system called Graptor, which is already faster than the baseline GAP code for the Twitter graph. And we've improved the execution time by a further 48% by using compact vertex properties. In the case of the UK union graph, the GAP code fails its own self-checks of correctness, and this is because the numerical accuracy in the GAP code is not sufficient to operate correctly on very large graphs like the UK union graph. So that's why it comes out as a fail. In comparison to Graptor, we obtain a 38% speed up by compacting the vertex properties to 16 bits. Similar observation holds for the accelerated PageRank problem. In this case, we compare to the Legra implementation, which provides a reference implementation for accelerated PageRank, and we obtain 40% and 33% speedups. We've also looked at architectural level metrics of the execution to validate what is happening. So we started this presentation by saying that we want to compact the vertex property arrays in order to fit more data in cache. Well, here we are measuring how effectively that cache is being used. So we have last level cache metrics, so the misses per 1,000 instructions for the last level cache is reduced from around 450 in the baseline code with 54% less than 300 for the Twitter graph, and we make a 42% improvement for the UK union graph. The data TLB, which caches address translations from virtual to physical addresses, is also significantly affected. So for the Twitter graph, we reduce data TLB misses by 94%, and for the UK union graph by 27%. And so these are the primary drivers for performance improvements that we have seen. We, however, have to pay a penalty, and that is the cost of the conversion code. And so these results apply to the PageRank problem, where I've shown the conversion code where we have 2 additional one-cycle instructions to convert a 16-bit pattern to a floating point number. And in this case, that means that the number of instructions that we execute per edge already increases by 24% and 27%. So even though we only add 2 instructions per edge, this already accounts for a fairly substantial increase in comparison to the baseline, because these graph analytics operations typically execute very few assembly instructions per edge to start with. And this is also the reason why we need to be extremely careful about the conversion code. So in conclusion, we propose that applications should be able to make use of software-defined number formats. By having compact number formats, we can improve cache miss rates and TLB miss rates. And by making the number format application specific, especially at narrow bit widths, we can avoid loss of accuracy during the computation. Efficient conversion methods are extremely important. We need to minimize the latency of conversion, minimize instruction counts, and maximize memory level parallelism. We want to have rich instruction sets because these have some useful instructions that allow us to do operations in a very short period. So AVX512 has much better features for this purpose than the AVX2 instruction set, which is also better than a scalar x86-64 instruction set. The techniques we have proposed for floating point number conversion can also be applied in part to integer data types, especially if we look at 1 and 2-bit integral data types. We can achieve speedups up to 89% for PageRank, up to 262% for the maximum independent set problem. And this is compared to vectorized execution on Graptor. So for further information, we can refer to websites by the group. The source code of Graptor, including the compact number formats used in this paper or in this presentation, has been published on GitHub. We also give here for reference a citation to the paper. Thank you for your attention.